Hi everybody, welcome back, and we are going to do notes number 10, Graphing Systems of Inequalities and Linear Programming. So you might remember from the end of chapter 2 when we graphed a linear inequality. So we make a dotted line, we make a solid line, we shade one way or the other. So today we're going to look at systems of inequalities. So we're going to have two lines, either dotted or solid, with their shading, and then we'll look to see where it overlaps, where the shaded regions overlap. And then we're going to do the application called linear programming. Okay, and I apologize if my lines aren't very straight because I really don't have a ruler tool at my disposal right now, so I'll just do the best I can. We're going to graph this system with y is less than or equal to 3x plus 2, and y is greater than the opposite of x plus 4. And I think I'll go ahead and color code them. So I'm going to do one of them in purple and one of them in green. And let me go ahead and put some axes in here on my graph. And looking at the values of the slopes and the y-intercepts, I think we would be safe here to go with a scale of 1s on both axes. Okay, so then the first line, we're going to draw the line first, so y equals 3x plus 2, y-intercept of 2, slope of 3. So let's get a few points in place. And because we have less than or equal to, because of the equals to, we'll make a solid line, not a dotted line. Now I'm going to figure out which direction to shade, but I'm not actually going to shade until I draw the other line. So if you have your equation in slope-intercept form and it's a less than, you can shade below. But if it's not in slope-intercept form, you wouldn't use that shortcut. You can also use the test point. So if I test 0, 0, it makes it true. So we know we're going to shade this one below, and I'm just going to draw little arrows showing I'm going to be shading it below. Now I'm going to move on to the second line. So the line is y equals the opposite of x plus 4. So y-intercept at 4. And slope of -1, we'll put a few points in there. And then because this one is greater than, but not greater than or equal to, this is going to be a dotted line, not a solid line. And then let's figure out the shading. So because it's greater than and it's in slope-intercept form, we would shade above. Or if you put 0, 0 in there, it makes it false. So we would shade the area that does not include 0, 0. So we're shading this one above. The reason I waited to shade was because I didn't want to make it terribly messy. So what does it look like if you shade as you go? You might have something like this, and then you might have something like this. And depending on if you're using colors or whatever, it might look really messy. So instead of doing that, I've decided that I'm going to wait and just shade the region that overlaps. And I'm going to go with a crayon because I think that looks like fun. The overlapping region is here. Now, the points on the purple line, this part of the purple line, the part I'm going to draw in red right here, those points are solutions, but the points on the dotted green line are not solutions. So everything in the shaded region and then everything on that red segment. Okay, let's move on. Here's number 2. So this time I have 4 inequalities and I'm going to graph them all together. And if we look at the values here, we have x is 10, we have x is 70, we have slopes that are positive. I think we're going to be focused on quadrant 1. So I'm going to draw my axes off center. And I'm going to let my scale be going by tens. 20, 30, 40, 50, 60, 70, 80. Kind of want to know where 70 is there. Okay. So now maybe you don't want to use 4 different colors. So if not, what if we just label them with either A, B, C, and D, or 1, 2, 3, and 4? I'm going to use 1, 2, 3, and 4, and you'll see why when we get to our applications. So first of all, we have the line x equals 10, and that's a vertical line. And because we have greater than or equal to, we're going to make it solid. Oops, sorry, that's not straight. And let's go ahead and plan to shade that to the right for greater than 10. And I'm going to label that number 1. And then for number 2, we have the line x equals 70. And then it's going to be less than or equal to, so we're going to shade that one to the left and label that number 2. For number 3, the y-intercept is the origin, so I'm going to make that point, and then the slope is 8/7, so I'm going to go up 80 and over 70, and that's also going to be a solid line, and that is 3. And then I don't want to try 0, 0 as a test point because that point is actually on the line. However, it is in slope-intercept form, so we can just plan to shade below for less than. And then finally, number 4, y equals 2/7 x also goes through 0, 0. And then for the slope, I'm going to go up 20 and over 70. So we have line 4. And that one is greater than, so I'm going to shade above. So if you put together all of your shading, you'll notice that you have a quadrilateral. More specifically, you have a quadrilateral with one set of parallel sides. We have a trapezoid. And what we're going to notice when we get to the applications is that the vertices of the trapezoid, or of whatever the region is, are going to be really significant. How would you find the locations of those vertices? Well, if you have 2 lines that intersect, you can make a system of 2 equations and 2 unknowns and solve the system, and you'll know the point of intersection. Okay, so now it's time to look at the problems that are called linear programming. Okay, I'm not quite sure the meaning of the word programming. It's not like computer programming. Linear makes sense. These are the steps that we're going to do in these kinds of problems. First of all, you're going to be given a word problem with all kinds of information, and it's going to ask you to find particular things. So identify your variables. Step number 2, you're going to have some limitations. It's going to say you can only make so many of these items, or people can only work this many hours a day, or whatever the case may be. Those are called constraints. They are limitations on the situation, and those will be written as inequalities. Step number 3, you have an objective in each problem. The objective could be to make the most profit, or to have the smallest cost, or something of that nature. So that's called the objective function. It's also called the decision function. Then you're going to draw a graph of all of your constraints. So your graph is going to look like a system of inequalities. You're probably going to get a polygon, and you're going to have most likely a shaded region in the middle. So from there, you'll identify the vertices of that shaded region. It's called the feasible region, and you'll understand why when we get to a problem. And then you'll be checking to see how the vertices fit into the objective function. That will make more sense when we get to a problem. And from that, you'll be able to determine the answer. Okay, so we're going to go through a couple of problems and walk through each of these steps. All right, so this problem says, a company manufactures 2 types of printers, an inkjet printer and a laser printer. The company can make a total of 60 printers per day, and it has 120 labor hours per day available. It takes 1 labor hour to make an inkjet printer and 3 labor hours to make a laser printer. The profit is $40 per inkjet printer and $60 per laser printer. How many of each type of printer should the company make to maximize its daily profit? Use the complete linear programming process. Okay, there was a lot of information in there. So the first thing I want to look at is, what is the question I'm trying to ask, or trying to answer? How many of each type of printer should the company make to maximize the daily profit? What are the types of printers? We have inkjet and we have laser. So I'm going to use a capital I for the number of inkjet printers. I don't want to use a lowercase I because I guess that could be something else in math. And also I want to put the top and the bottom on the I because I don't want it to look like a 1. And then I'm going to let capital L be the number of laser printers. And again, I'm going to make that a capital L, not a lowercase l, because I don't want it to look like a 1. Okay, the first step was identify variables. We've got that step done. The next step is to write the inequalities or the constraints. So what are the limitations on the situation? Okay, so there's a few things we know. We know that the company can only make 60 printers per day. So we can write I plus L is less than or equal to 60. Okay, we also know that they have 120 labor hours per day available. They don't have to use them all. It takes 1 labor hour to make an inkjet printer, and it takes 3 labor hours to make a laser printer. So for that we can write 1 times I for the labor hours per inkjet times the number of inkjet printers, plus 3 times L for the number of hours per laser printer times the number of laser printers, and that's going to be less than or equal to 120. They don't have to use all of those hours, but they can't go above it. Okay, we also have some invisible constraints. Because you cannot make a negative number of printers, I has to be greater than or equal to 0, and L has to be greater than or equal to 0. Always include those. So here we have our set of inequalities. We have 4 of them. Step 3 is to write the objective function. What was the objective? It's to maximize the profit. So we write profit equals, well, let's see. We get $40 per inkjet printer, so 40I plus $60 per laser printer, 60L. Okay, the next step is to graph the constraints. By the way, I noticed a moment ago that I forgot to put my L on my profit. So profit equals 40I plus 60L. Okay, so now for the graph. Because I is greater than or equal to 0 and L is greater than or equal to 0, we're going to be using quadrant 1. And I'm going to label each of these as 1, 2, 3, and 4, just like I did in the previous example. And for number 1, I'm going to find the intercepts, so it's easier to plot. So if I is 0, then L would be 60, and if L is 0, then I would be 60. And for number 2, I'm going to find the intercepts as well. If I was 0, L would be 40, and if L was 0, I would be 120. So that helps us know what kind of scale to use for our graph. So I'm going to go ahead and draw my axes. And if you make your graph really, really tiny, it can be difficult to maneuver with so much information going on. So give yourself plenty of space. Okay, so we need to be able to go out as far as 120. So I think I'm going to go by tens on my x-axis. And I'll just go by tens on my y-axis also. Okay, so now let's go ahead and graph. We have, for line 1, we have the point 060 and the point 60. Again, please use a ruler if you can. It's going to make this so much better. And label that with a 1. And that is going to be shaded below. You can test 0, 0, and it makes it true. For line 2, we're going to plot the point 040 and the point 120. Use a ruler. And that's line 2, and that one also would shade below. Line 3 is the line I equals 0. And remember, I chose to use, well, I guess I didn't say, but I'm using I as my x-axis and L as my y-axis. So that means that the line I equals 0 is actually vertical. It's the y-axis. So there's 3, and that would be shaded to the right. And then L equals 0 is the x-axis. Be sure to show that you're drawing those lines. We don't want to just assume that they are there. So if you then shade, you're going to have this region down here, this little quadrilateral. So let's look back at our steps. Identify the variables, write the constraints, write the objective function, graph the constraints. Okay, identify the vertices of the feasible region. So the feasible region contains all the points that could be solutions to the system. All the points on the boundaries, because the boundaries are solid lines, and all the points in the interior that we shaded. All infinitely many of those points are solutions to the system, but which point gives you the highest profit? The goal is to find that. Well, what happens if you move from the point 0, 0 up to the point 0, 40? What's happening to the profit along that boundary? It's going to get bigger. What happens if you move from the point 0, 0 to the point 60, 0? The profit is just going to get bigger. So it makes sense that it wouldn't be a point in between the vertices. It makes more sense that it would be a vertex. And then if you were to test some points along the other boundaries, going from the point 0, 40 over to whatever this point is, the profits are changing in between. And then from the point 60, 0 and over to this point over here, the profits are changing as you go in between. So what we need to do is take each of those vertices and find the profit for it. I'm going to label those vertices A, B, C, and D. And yes, we know that it's not going to be A, it's not going to be 0, 0, but for the sake of thorough mathematics, let's include all the vertices. So what I'm going to make is a little table which shows the vertex and its corresponding profit. Okay, so vertex A is 0, 0, and the profit would be $0. Vertex B, we know from graphing, is the point 0, 40. So $0 for every inkjet printer plus $40 for every inkjet printer, 40 times 0, plus $60 for every laser printer, 60 times 40, is going to be $2,400 profit. I'm going to come back to point C. Let's do point D since we already know it. That's the point 60, 0. So $60 for every inkjet printer, oops, I keep saying that wrong, $40 for every inkjet printer times 60 printers, plus $60 for every laser printer times 0 printers is also $2,400. Now let's find point C. So it's the intersection of lines 1 and 2. So what I'm going to do is take line 1 and line 2 and find the intersection point. The equations were I plus L equals 60 and I plus 3L equals 120. So suppose we use elimination and we subtract the two equations. We will have negative 2L equals negative 60, so L equals 30. And substituting that back in, we get I equals 30. Now, does it seem to you when you look at your graph that that point could be the point 30, 30? That seems logical to me. So C is 30, 30. Okay, $40 per inkjet times 30 inkjets, that's $1,200. $60 per laser times 30 lasers, that's $1,800. So altogether, $1,200 and $1,800 is $3,000. Okay, what's the next step? Identify the vertices, substitute vertices into the objective, determine answer. Let's determine the answer. Which set of numbers gives you the highest profit? 30, 30. So we can say the company should make 30 inkjet printers and 30 laser printers for a profit of $3,000. Okay, so there's an example of how you would do a linear programming problem. Let's not make the assumption that it's always going to be this vertex here, that's the answer. It's not always the case. In the simpler problems, it's often true, but the problems aren't always simple. So, what's going to happen next is I want to work through a second example. I feel like it's going to make this video way too long. So I'm going to stop this video and then I'm going to make the other one in part 2 and we'll work through the second example.